What?
So it's nothing yet to do.
Oh, it's free and it's good. I'm going.
Yeah, but you were.
Because I know what it is.
What is it?
I'm not telling you.
What?
But just,
Be there.
I'm going. I think it'll be good. Huh?
We'll be there.
If have food.
I don't know. Can I tell them this? Do you know if there'll be food or not?
Yeah. Yeah, it will be, but not.
No, the email didn't know it.
All right. I won't say anything then.
Okay, then that means there is food.
No? maybe not. Who knows? I need to read what it says on your poster. Okay, waves. Which one are we on? We just finished
Now it's 3.
electromagnetic, so now it's 3, yeah.
But in the hard. Okay.
Everything was useful in the ICT for your maths coursework. Is it nearly finished, the maths? Yeah. Yeah. And how was the maths coursework? Did you all manage to finish it? No? So nearly finished then, yeah?
I don't know how to do task 3.
Yeah. It's due on Tuesday, isn't it?
Yeah.
Who's your maths teacher?
Or
Do you have him today?
No.
no.
Have him on Monday?
No, he said that you can email me like if you have any problem.
Good. That's good.
But not on Monday.
Not on Monday, because my mother could go, yeah. Okay, you write this down. That's what we're doing. What are you doing in chemistry right now?
Group friend. No, group number 2. That is group 2?
Group friends.
Yeah.
We haven't started that yet.
We have yesterday. Another session we have started.
Finished the lecture.
Yeah.
Oh, you did electronegativity? Yeah, okay. Right, reflection, diffraction, refraction. Sorry, do you have this?
New notebook for chemistry. Take one more minute.
So, the first one, reflection. You got your problem sorted? Yeah. So still no Andy? Yeah, okay. Was he? Maybe he's just skipping physics days. Right, reflection is a change in direction of a wave at a boundary between two different media. So as the wave moves back into the medium it came from. The most common example includes reflection of light against a mirror, sound and water against a wall. So it's reflection. The light, when it hits the boundary, comes back to the medium. Do you remember last week? No, sorry, this week we were saying medium. Like air is a medium. What else is a medium? Do you remember? Water is a medium. What else is a medium?
No medium for gamma.
No medium for gamma. True, yeah. Do you remember what else is a medium? Air is a medium. Water is a medium. Table, earth. You're looking up medium. Now, I don't know if that would be successful. So anyways, you don't need all of this for the exam. Guys, for the exam, if you ever get asked this, you don't usually. The first sentence is enough, okay? And the example, you can write it down if you want. Did you translate medium, Fawn?
It has many meanings.
Many meanings, yeah. Medium means something a wave can travel in. You know?
I think that...
Here, when I speak, the sound wave moves in the air. If I'm in the water and I hit the water, the wave moves in the water. Air and water are mediums because waves can move in them. Yeah? Light
So it means like go between.
The
The
thing it goes
Yeah.
between, yeah. You look so cold.
I'm blue.
Oh dear, that's why you have lancet.
Yeah.
Yeah.
-1 degree.
It's okay.
No, I
The
never-
important thing is it's not windy or raining, so it's not so bad.
But it has ice.
A little. Just a little.
The first time in my life.
Really?
Yeah, in my country.
No ice?
Yeah. The lowest temperature is 7 degrees.
Really? So it's a new experience for you. Probably the same for you guys, huh? Yeah?
It's too hot actually.
Too hot? I think it's fine.
It's better than
It's-
sweating.
Yeah, this is much better than being too hot.
Yes.
Would you rather be too hot or too cold? I think too cold.
Well, I feel that's
More
what I
than
want.
Yeah. Fail. Alright, can we go on to the next definition?
Yeah.
Yep. Okay, so the example is the mirror, is the common example. Yeah? Yeah? Okay.
Is this a nice calculator? This one?
Yeah, it's not as good as the Casio 991. Diffraction. So diffraction occurs when waves bend around small obstacles, or when waves spread out as they pass through small openings. So this is an example of diffraction. When the wave travels through a small hole, it will spread out. If the hole is big, it doesn't really spread out.
That's a double slit.
Yep, it is exactly the same as a double slit. So when the wave travels through a small slit, it will spread out. This is called diffraction.
Okay.
What does bend around small obstacles?
Yeah, it's like sound wave. If it hits the cup, it doesn't like it can bend around the cup. You know what I mean? It's not like
It doesn't bounce back.
it doesn't bounce back. It's kind of like wraps around it. Yeah, diffraction is usually used in this situation though. It's more common for what we need. Yeah,
Let me draw down.
I think you should draw that, yeah, it'll be helpful.
Different.
Yeah, what I'm saying is if the hole is big, no diffraction. If it's small, much diffraction. Much.
This also has different.
Hmm?
This also has, but it's
Small.
Yeah.
Yeah. Yeah? We got that? Yeah, continue? Okay. So, the last one is refraction, and that's when the wave changes direction. And this is because of a change in the wave speed. So, refraction, you see it most when a wave passes from one medium to a different medium. So for example, when the light travels from the air to the glass, you see how its direction changes. And then when it goes from the the glass medium to the air medium, again it changes its direction. So this is called refraction. A change from air medium to glass medium changes the direction, and glass medium to air medium changes the direction again. This is called refraction.
And the prism.
Prism, yeah. There's, the light going through the water.
And then
Yeah. Many examples. Now the reason it changes the direction is because here the light actually slows down in the glass. Last class we said the speed of light is c.
Yeah.
This is still true, but this is only true inside a vacuum or empty space. But when light passes through mediums like glass, it slows down always, and this is what is causing the change in direction.
Always is causing the change.
The example that's always given is if a car is driving very fast on a road and then it goes off the road into mud, the speed suddenly slows down because the car can't go as fast on mud than it can on the road. So when the car leaves the road, it doesn't continue in a straight line. You notice it always kind of swerves.
Yeah, but it's because it slips. This is light through less.
No, I know, but it's not because it slips, it's because it's going slower.
Even
And
in,
it's
even in a straight line, if there's
Light-
one in front of the
light-
road, if you keep going straight, you'll still slow down.
Like,
This is the second car example, and I don't drive, so you remember the first.
Yeah, I do.
And the electron can move in the air easy, but in glass is screen the light to go faster, so it's slow.
It slows down.
Yeah, it slows down, but why does the direction change?
The reason is, it is a bit like the car, but you don't have to think about a car. It's going fast here, and when it hits this one, I suppose it is, the car would be a good example, although it's not exactly the same. When the car is going off the road, the first wheel hits the mud before the driver's wheel.
Yeah.
This one slows down first before this one, because this one hits the boundary first. So when it hits the boundary, this one slows down, which causes the sudden turn off the road. Now, if this light was perpendicular to the glass, it would go straight. It's because it's at an angle. It's almost like the left part of the light slows down before the right part of the light because it hits it at an angle. And this is what causes the change.
Why does it spread out? And
When
the
it-
glass? I mean, the slower part.
Spread out. No, do you know what? It might actually spread out a little bit. It's just not enough for us to see. Do you mean the light spreading out a bit?
Yeah, because.
Yeah, I think it does. I think it does spread out a little bit, but we can't actually see it. It's too small. But you. Oh, and the other reason is it's because of this red light. It's easier to see the spreading out with white light because then it produces different colours when it spreads out, like the prism. Yeah. Anyway, so continue. Right, can I go on?
No,
Yeah.
second.
Ah. Yeah.
Yes.
So remember I said because it's travelling through the glass, it's travelling slower. Remember that? So we have this concept called refractive index. Some materials it's easy for the light to travel through, and some materials it's harder for the light to travel through. So for air, it's very easy for the light to travel through, so it doesn't really slow down. But for glass or water, it slows down a little bit. We use something called refractive index to measure how much it slows down. So for example here, refractive index is how fast the light can travel through the material. So as a formula, it's C over V. C we did last time, and V is the speed in the medium.
So it's the speed of light upon over
The speed in the material. Now wait, before you write this down, I want you to tell me, will this be bigger or smaller than 1?
Smaller.
Bigger.
Bigger?
Yeah.
Because I said it always slows down. So the V is always less than the C.
Yeah.
Okay.
So that makes it bigger than 1. Because the top is bigger than the bottom.
Yeah.
So n is always a number bigger than or equal to 1. In fact, 1 to infinity. If n is 1, we have empty space. If n is infinity, it means the light has stopped moving, because the speed is 0. We won't deal with that.
I should write the last thing.
I know, really, this is what you want here.
Will we do this in the lab?
Yeah, we'll calculate this in the lab.
Yeah, like we will put acids and
Acid?
Yeah, just a minute, and then we put the
We'll use a laser and water.
and then it will show.
Okay, you got this?
1 second.
Is there any lab in the college?
Any what?
Lab.
No.
Okay, so how we will go to the lab?
I have the equipment in the office. I'll bring it to the classroom.
Oh, okay.
We used to go to a lab
There is
And-
any lab in the building.
in DIT. We used to use that lab. Then I discovered how expensive it was, and I said, no, I'll do it cheaper. Because DITs, they said, like, it's like 800 euros to do the experiments. And I'm like, okay, well, just give me 200 euros and I'll buy the equipment, and we can do it in the classroom. Because you're paying 800 euros every year.
You can.
This is expensive.
Or something you can
Yeah,
use.
you pay 200 once then.
You need to be fancy about
Yeah.
I didn't think it was good value because the experiments weren't exactly like, fancy. You just had the trolley and, circuit. But I bought, the voltmeter and the ammeter, they're only like $10 each.
Wow.
They're really cheap. The digital ones, really, really cheap. So, and a resistor. I bought a resistor off of eBay, a pack of 3 resistors for €1.
For €1?
Because it's only a little resistor, I got a battery off of Sylvia,
That's a donation.
Yeah. The most expensive piece of equipment was a box of weights for the Newton experiment.
Yeah.
For some reason, the weights were really expensive. Like 1 kilogram, 500 grams, a box of weights.
So they are so good, like small ones.
Yeah, the small ones, 5 grams, 10 grams, yeah. Okay, you wrote this down?
it. Yeah.
Yeah.
Two of the lab or the speed.
The 4 experiments, yeah. There'll be pendulum, Newton's second law, F equals ma, with the car, the trolley.
Yeah, and the Newton first law.
No, not doing that one. We're doing the electricity,
Yeah.
the V equals I or. We're going to use the graph to calculate the or, the IV graph. Yeah. And then the 4th experiment is what we're doing today, is the waves calculating the n. Yeah? Okay. It's okay, be strong. Right, so we have this law called Snell's Law, and Snell's Law helps us to calculate, let me show you. Snell's law helps us to calculate the angles here. The angles. So, Snell said, one form of it is that sine theta 1 over sine theta 2 equals n2 over n1. So you have the two different materials like air and glass. So you have n1 and n2, and then you have one angle, theta 1, and then another angle, theta 2. Now I'll draw all of this, don't worry. Okay, let me draw this. So let's say here, it doesn't matter, let's just say this is air and this is glass. And this is the separation between them.
But light will transfer one to
No, I'm explaining something, so you need to
No,
listen. No, listen. You can ask questions at the end of the explanation, okay? So the light travels through the air, and let's say it hits the glass here, and I call this angle theta 1. Sorry, that is not theta 1. I should also say that we always measure angles not with the boundary, but with the line that's perpendicular, which is called the normal. And you might know this word from maths. Normal is perpendicular to tangent. Do you remember? Have we done that word? Yeah. So this angle here is theta 1. And then, whatever, I'll just draw it here. And then this angle here is theta 2. I know, it's ugly, sorry. It should be bigger, isn't it?
Yeah.
Okay. Theta 2. Theta 1. So Snell says that if you calculate sine theta 1 and divide it by sine theta 2, that would be the same as if this material is n2 and this material is n1, n2 over n1.
Why is it like this, not like this?
I don't know, because I have to calculate the angle.
I think it's because it should be like this because...
Hang on. If you give me a few seconds to think, I can think about it. So a value for n1 would be something like 1.01, and for n2 would be 1.3. So actually, I think it should be smaller, not bigger.
No.
Yeah.
Well, do you know what? We'll just calculate with an example. Yes?
You don't need numbers.
We'll do an example. Actually, yeah, you can do this one for me. So, you have n1, you have n2. Let's say theta 1 is, what angle will we say that is? What does it look like? 45 degrees?
Yeah.
7.
Well, just say,
30.
okay, 30. Theta 1 is 30. Calculate theta 2, please.
Oh,
1.01 and 1.3. Sine 30 over sine. Interesting. Is that bigger or smaller? Go on. 1.3 over 1.01, and when you solve this, you got theta is 20.
23.
23?
22.3.
Okay. So that's actually smaller. That's interesting. Very interesting.
just like I meant.
Yes. Okay, continue.
But when is bigger?
Huh?
When is bigger?
Bigger is when this would be smaller than this. So, for example, if we go from glass to air, it would be bigger. Yeah? Alright, let's continue. That's one formula. There's other ways to write Snell's law. Another way to write it is like this. Oh, sorry, I should actually give you some more vocabulary. This theta 1 is sometimes written as I, and the theta 2 is sometimes written as or. And the light that comes in is called the incident, and the light that comes out, refracted. You should write those 4 words down. I and or, and then incident for in, and refracted for out. Yeah, now we're talking, yeah. You know this? Good, write it down.
Which one is which?
Oh, you're making me say it 3 times. This is the incident, and this is the refracted. We're good?
It's okay if I write alpha instead of theta.
You can write, if you don't want theta, you can write I and or. Got that? Yeah. Continue? Sorry, continue?
Yeah.
What are you writing? You're drawing the picture. Okay. What are you doing in maths at the moment?
Integral.
You're doing what now?
Integrals.
Integrals? What was the last? Did you do area
Yes.
with integrals? Yeah. So next lesson is probability, I think.
We
But
check
something in
41.
area.
But this is, I don't, like, in many questions there are graphs. These are really like, I can't understand them at all.
Yeah, I don't know. I don't know who made that workbook. Maybe you look at the name on the bottom of the pages. You can contact this person and give them some advice.
Yeah, or reflect on them.
Yeah.
And the worst thing in this workbook is the graph for the, the higher and the lesser values.
The minimum and maximum. Too much. Too
I
hard.
have done maths, but I have never done this thing to make the graph. And then you plot the values over.
So you should send an email thanking the person who made this book, saying, "Thank you for showing me maths I've never seen before." All right, continue. Now, there is possible to have an angle for theta 1 so that theta 2 is 90. So what I mean is, let's draw it like this. Let's imagine that this here is air, and this is water, and this line here is the normal, and the light comes from the water. So it comes up here, hits here. This is theta 1, and I'm going to call this C for the moment, because we can find a special angle that makes the light not escape and instead run across the boundary between them. And in fact, if we were to go past this angle C, the light would come back into the water. It'd be reflected back in. So this special angle where this happens is called the critical angle. And you can easily calculate it because you have sine C over sine 90, because you want a 90 here, equals N2 over N1. What's sine 90? It's 1. So C is just sine inverse N2 over N1. And this is the critical angle. But you'll notice that N2 must be smaller than N1, because if you ever try to calculate something that's bigger, this doesn't work on the calculator. So this is the formula for critical angle, which I think I write here.
Can you repeat, because when I tried to do the first question? before. Sine inverse.
Huh? Sine inverse of this?
No, the first question, the first example. I was writing.
But I didn't give you any numbers.
No, 1.01,
1.01.
Yeah, but if you put 1.03 over 1.01, what do you get?
1.0. 0.77.
No, you have that upside down.
Yeah.
1.2.
Yeah, and you see, you can't use that formula here because it only works when the N2 is smaller than the N1. Here the N1 would be, for example, 1.3, and here the N2 might be something like 1.01. So as long as the N2 is smaller than the N1, this can happen. This is called internal refraction. So, I didn't write the formula down. Well, this is the formula here for it.
For the critical angle.
For the critical angle.
The definition.
The definition, it's the angle required to make 90 degrees when refracted. The critical angle for the incident will make, or will cause, I should say, how do I want to say this? The critical angle for the incident is the angle required to make 90 degrees what's my preposition? To make 90 degrees in the refraction or something.
So from the moment it goes with the water and down.
Yeah, so what happens here is if you're at the critical angle, the light doesn't escape, it travels along the boundary. And if you're past the critical angle, it actually refracts back into the water.
And both are critical.
Now, technically the critical is the point at which you cause it to go on the boundary here of 90. Yeah? In fact, we'll do this experiment and we'll see this in the lab where we move the laser until we hit the critical angle and the light travels along the surface of the water. Yeah? Yeah? No? What's your question?
What you talk?
No, nothing much. Alright, continue. Notice in the last lesson when we were looking at the electromagnetic spectrum, we had red, orange, yellow, green, blue, indigo, violet colours. We didn't have the colour white, did we? No. And that's because white actually is all of them. There's no frequency. White light is all the colours combined, red, orange, green, etc. So white light is a mixture of all the colours. That is, when red and orange and green, etc., etc., are combined, the result is white. So another way to state Snell's law is by using wavelengths. You can say sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. Now note, please be careful. In the previous version we had n2 over n1, but in this one it's lambda 1 over lambda 2. So please be careful. Please be careful with that. Can you write this down as a different version of Snell's law? Yeah? Do you have your table from the last class with the electromagnetic spectrum in it, with the numbers? Yeah? So watch this. So imagine I have, I don't know, some glass here, and this is air. So again, we'll just say N1 equals 1, and here we'll say N2, I don't know, equals 1.5, something like that. And we have white light. But white light is just a mixture of all the colours, isn't it? So when I have white light, it's like I have, it's like I have red light, but also that I have all the other colours. So for example, like blue light as well. I won't draw all the colours, I'll just do red and blue, okay? Now, these have theta 1. So let's have a look at what happens with the blue light. You have sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. And then with the red light it's the same.
Now they will separate.
Yeah, sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. Okay, now actually, is there another formula I want to give you? Because I don't know if this is the one. Yeah, this will make a difference. Yeah, okay. Right, so if you look at that table I gave you, which has the bigger wavelength? The red or the blue? If you have a look at the numbers I gave you. You don't have it?
I have blue is 5 multiplied.
Yeah, but between red and blue, which one is bigger?
Red is 7 multiplied by 10 minus 7. Blue
Hang on, red. Let's do it in red. Red is 7.
by 10 minus 7.
This is the wavelength. Yeah.
Yes.
Meters.
Blue is 5 by 10 minus
5 by, what is it?
7. 10 minus
10 minus
7.
7. Meters. So which one is bigger here?
Blue.
The blue. No, try that again. Which one is bigger here? Which is
7.
the red? The red.
Oh, it's 7 times 10. Okay.
Yeah, 7. Yeah, yeah.
Yeah, yeah.
Let me just have a look at my picture here. Yeah. Yes. So here, which is bigger here, the lambda 1 or the lambda 2? We said the blue one is bigger. Now, sorry. We said the red one was bigger here, so this one is bigger than this one here.
Yeah.
So this one is bigger. The theta ones are the same, aren't they? Theta, like it's the same angle for both of them at the start, so I'll just write this one is the same, and this one is the same. And it's the theta 2 that we really care about knowing here. So, if you think about it like this, if these are the same, but this one is bigger, then do I need to make this one, you know what, it's going to get a bit confusing, let me just rewrite it. Sine theta 2 equals lambda 1, lambda 2, sine theta 1, and here sine theta 2 equals lambda 1 over lambda 2 sine theta 1. This one is bigger than this one, which means this one here will be bigger than this one, because on the right it's bigger.
Yeah.
So that means that one will be bigger than this one. So if the sine is bigger than the angle, it's also bigger than for this one. So it means when I draw it, the bigger one, the red, will have a bigger angle. So this angle theta 1 will be bigger than the blue angle here, sorry, theta 2 will be bigger than the blue angle theta 2. So what will happen is the lights will separate with different angles. So here you'll get red, and then the next one will be orange, yellow, green, blue. Blue is further down. So you'll get the rainbow here. And if we look here, that's what we get: red, orange, yellow, green, blue, indigo, violet. Because the angles for these ones will be bigger than for the angles up here. Because the wavelengths here are bigger than the wavelengths here.
Are the angles constant, or does it depend on sine theta 1? It depends on sine theta 1, doesn't it? Like from where the light is incident.
Oh yeah. So I mean, if you change the sine theta 1, you'll change these angles here, but the relationship still holds that because the wavelength is bigger for red, it will have a bigger angle, which means it will be up higher. And the wavelength is smaller for blue, it will have a smaller angle, so it'll be down further.
So
Even if you change this, it won't change the relationship here between them. Yeah?
So the wavelength is going to stay the same if we change the sign?
Which wavelength?
The lambda?
Which lambda?
Any of those, and we change it.
The wavelengths are constant, aren't they?
Well, the wavelength here is for the red is bigger than for the blue.
Yeah.
Constant?
It's constant, yeah, for all the colours, yeah, they're constant, yeah. Now, other stuff happens here. I haven't talked about exactly what's happening with the lambda 2.
Yeah.
Lambda 2 will change.
It will, yeah, so I'm kind of fudging it a little bit here to try and simplify the explanation. The lambda 2 will change, but I just wanted to give you a simple explanation for why they separate like this. And because of different lambda 1s, it means in the formula the theta 2 will try to be bigger because the lambda 1 is, for example, bigger or smaller.
But they all go in at the same speed.
They do, but because they have different wavelengths, they'll all have different angles when they exit. Because another version of Snell's Law is this one that says the relationship between the angles, you can find it from using their wavelengths.
Okay, what is lambda 2 here?
Lambda 2 is the wavelength after the light passes through. So actually, I didn't want to complicate things, but it actually changes colour when it passes through as well. So the red...
Because it's slower in the water, and then it's faster in the air, is why it changes color?
Yes. Well, yes. Ish. Yeah. The whole reason... Yeah, well, at the end of the day, the whole reason all of this happens, the change in the colour, the change in the angle, it's because of the change in the speed, at the end of the day. So if these two materials, if this was, for example, 1.6 and this is also 1.6, the light travels at the same speed in both, and then none of this would happen. So it is because of the change of the speed then.
But why is it yes-ish, not yes?
It's more complicated than how I'm presenting it.
Okay.
But I just need to present it complicated enough for the exam. Yeah. In the exam, this formula isn't even on the course. The only formula on the course is the previous one. Yeah. But I wanted to show you this one to give you an explanation for why the light spreads out in the prism. But it's not something you need for the exam. Prism. The different colours inside will have different lambda 1s, so they will refract differently. Okay. Here are the three ways you can state Snell's law. The first one is the most common and the most useful. The second one I just did, but there is another way to state it using the speeds. Sine theta 1 over sine theta 2 is v1 over v2. So these are the three ways you can state Snell's law. The most important one, the first one. Second most important, least important.
Are they in the exam, the second one?
I've never seen them in the exam ever. I've only ever seen the first one. Yeah. Got these? Okay. So one use of Snell's law is making a lens, like on your glasses. When light enters glass, it will refract. But the lens is curved, so this will result in different values of theta 1 and theta 2. However, the lens is carefully made so that the refraction will cause the light to converge. So I'll explain here with a picture. So, where's my pen? No. One second. Oh, no, it's back. Right, so you know, here's my lens here. It's beautiful. Now this here is air, and this here is
Water.
no glass
Length.
lens.
Length.
Yeah. So what happens if this light comes in at an angle? Well, let me draw the let me just draw it here. So here's the light coming in here at an angle. The normal is perpendicular. So if this is here, this would be the normal, for example. The light bends, doesn't it?
Yes, up.
Does the angle get bigger or does it get smaller?
Bigger.
Where is the angle? Smaller.
Smaller. This is theta 1. So theta 2 here will be smaller. Now the lens is specially made so that what happens when the light comes in and hits it and refracts, the design of the lens is so that all the refracted light meets at one point. So the curve here...
Doesn't it change the direction when it leaves the...
Yeah, I know, which I haven't drawn in the picture, but I mean, I'm trying to keep it simple, but you're right, it changes direction when it leaves, but no matter, it's designed, well, sorry, it's ugly, I know, it's I know, it's designed so that the light, when it exits, always meets at one point. So this curve is very carefully made. There's only one shape that will do this. It has to be just the right shape so that all the light will meet at the one point. I think the shape is kind of like an x squared shape or a root x shape. I can't. This one here, yeah. This one kind of has a root x shape to it. If you were to graph root x, the graph looks like this. I think the shape of the lens is kind of like this. Anyway, that's not important. What I'm saying is we can use refraction and a curved glass to make the light meet at one point, like at the picture here.
Does the distance change it?
What do you mean?
Like if this is the lens, this is the paper, does this affect?
No, it doesn't. The only difference is if the paper's too far away, the light will meet at this point and then they'll separate again.
Oh.
Well, if you think about it like this, if the light's coming this way, and it's coming this way, and then it's coming this way, and meets here, if I put the paper here, I'll see a circle on the page. If I put the paper right here, I'll see a dot. And then if I put the paper back here too far away, it'll come back to being a circle. So you adjust it then.
Yeah.
Yeah? Okay. So it's just one application of Snell's law is for making a lens. For the exam, that's all you need to know. The question would be, what's an application of refraction? Making a lens is one example. Okay. So let's have a look at some questions now. Can we go on? So I think it's just the one question to do, but I broke it into a few parts. So if you can write this down, please. You're not writing it down? If you don't want to write it down, you can at least draw it.
I'm solved.
Or solve it. I'm going to do it in a minute though.
C multiplied by 10 to the power 8.
Yeah. Ooh.
It's all the same formula, right?
Hmm?
The same formula.
What's the
No units, they're unit free. Let's have a look. So, firstly, I tell you, when you have some glass, the red light moves in it with a speed of 2 times 10 to the 8. Be cool now, be cool. Meters per second. This is less than the speed c, isn't it? Yeah, because it's travelling in glass. So, first question is calculate the n. N equals c over v, which is 3 times 10 to the 8 over 2 times 10 to the 8, which is 1.5. So that's the first part.
Why you have C? Why you have C?
3? Yeah? 3 is for the c.
Yeah, why you have it?
I did.
Because we did this in the last class. For the c.
C is always.
Constant,
Yeah.
always gonna be first.
Ah, yeah. Right.
C is the same.
C is the same, yeah. Okay. B part? The light, red light enters glass from air at 20 degrees. What angle does the light travel at after entering the block? So what you have here is, you have some air where the N1 is equal to 1. You have some glass, and you know what the glass is, we just worked it out, it's 1.5. Here is the normal.
No, but in question, they did not give us the 1.5.
Ah! It says, red light enters a block of glass. Question A, what is the N for block of glass, for glass?
Oh,
Yeah. Right. What did I say? It comes in here at an angle of 20 degrees, and we want to know the angle that it leaves at. We'll call this angle, let's call it R. Sine 20 over sine R equals 1.5 over 1. See what we get.
And 20 divided by 1.5.
Mm-hmm. I want it in degrees.
So,
13.8.
1
Mm-hmm. Okay. It's all okay so far, isn't it? Now C, the last part. Some light is shone from glass to air. What angle should it shine at so that it's a critical angle, basically? So this time now, we have it from glass to air. And the light comes in, hits the air from the glass, but this time then travels along the boundary. And what do we call this angle here? That's called critical angle C. Now be careful, here the N1 is 1.5 and here the N2 is 1 because it's going from glass to air. So the critical angle is sine inverse 1 over 1.5, which equals.
How did you know it's critical?
I'll show you now. So I think in the question it says, some light is shone from glass to air. At what angle should the light be shone at so the light refracts back into the glass? So actually, I suppose you should really say anything greater than this would do it. No, you can't have greater or less.
No, greater, I'm asking greater or less. Which?
Greater.
No, not equal, only greater.
Why what?
Why Why that?
Why greater?
What's greater?
It's only greater, not equal, because equal will go with the...
Equals the boundary, so they'll allow that in the exam.
Yeah, why?
Why what?
Why?
Instead of what?
Why?
Fine, okay, fine. Does this make you happier?
No, I just asked why.
Oh, why this?
Not
Because
equal.
I want to... I want to know when the light will come back. So it needs to be bigger than the C. If it's equal to the C, it'll be on the boundary, which is okay. Is it okay? I hope so.
So when the question says refract back, you mean like a critical angle?
Yeah, the critical angle is the boundary at which it's coming back. Okay. Continue? Yes? Right. So, I think what we'll do is, because of the time, what we can do is I can let you do these questions and then I can do the answers on the board. And again, that means then no homework. So this gives you plenty of time for your other things to be doing. Maths and so on. Okay, so, yes. And don't forget mechanics. Right, you can start on these now. Can I close this? You can open it on your phone if you want, or take a picture if you want. Close my screen.
This picture? Can I take?
Yes, please.
My phone.
What?
Accepted.
What?
It's finished. The phone is finished.
Congratulations. Do you have your laptop? Yeah, you also have your laptop because you were in ICT.
It's out of charge.
Have you got your plug?
No.
Sit beside someone then.
Can I try to for the physics? Like,
I want you doing these questions because I'm going to do them on the board in like 10 minutes.
Oh, all right.
Well, I don't know. I think 10 minutes about, maybe. Actually, you might be able to unplug it. Can I? Yeah, unplug the projector. We'll save power.
So after that we not study.
What are you talking about?
After the homework.
After the homework, I'm going to do the answers. I'm not in a rush to get through the next class because you can leave it off. Yeah, just plug it back in. After I do this homework, then there's only 2 lessons and 2 homeworks left.
So sir, we have plenty.
Yeah, so we'll get them finished Monday, Wednesday, and then Friday is the test,
Yeah.
and then the following week will be revision.
Revision. The whole week.
Yeah.
What's the reason?
Why
You
don't
are-
you answer something?
Huh? Yeah.
That is right. It should be big.
Really?
Yes.
Speak?
The speed of the radio wave. Yeah.
Oh.